Hey all, so we're back here with the practice final exam. Hopefully you all did okay on the midterm. Historically, people tend to find that more challenging than the final. I thought it was the opposite for me, so you might not agree with that, but most people say the final's easier. So for number one, we're asked to find the Fourier transform. And for this, before we start, I just want to recommend to all of you for your formula card for the final to go to the final review PDF that Professor Wang posted and make your formula card the first 7 pages of that. The next 8 pages are the property tables, which you get for free on the exam. The first 7 are kind of like going over everything you've learned so far. So you can scale those down, 4 on the first side of the paper and 3 on the back. And you'd have all the info, and you should use that sheet to solve the practice exam so you know where everything is when it comes time to take the real exam. Otherwise, your other option is to print out, or I'm sorry, not print out, to write out your own. I recommend you print out the first 7 pages and scale them down so they all fit on one page, but I guess it's ultimately up to you. Okay, so number one asks us to find the Fourier transform, and A is given by A is given by A x of t equals d dt Okay, you could use the definition for this. I don't recommend you do. Like I said, you're given the tables and the various properties for a reason. No one really uses the definition for the Fourier transform, at least mostly, to find the transform just because it's not convenient. So when you see ddt, you should think j omega. So x j omega is going to be equal to j omega, and we'll call this y j omega. This is y of t, this little bit right here. You see, because we're breaking down the function, so this will be y j omega. Okay, so we have a tabulated transform for y, and it's just given by when we have something that looks like this. Let me get this right. We have something that looks like this. The Fourier transform, which we usually write like something like that, is just going to be 1 over j omega minus a. Okay, so using this transform guide, we're just going to get x of t equals j omega 1 j omega. In this case, a is minus 3, so we get plus 3. And that's the final answer. Okay, now let's go to B. Okay, it says y of t equals e minus 3 t minus 2 u t minus 2. Okay, we have a property for this, so I'm going to go to my properties and tables, and this is called the shifting property. So the shifting property is in table 4.1, and it's going to be 4.32, and it looks, this is time shifting obviously right here. So we have a shift of this t naught. The way it's going to affect the transform is that we're just going to multiply the transform by j omega t naught. The exponential of negative j omega t naught, that is. Okay, so now we can just apply, we know from the past example that e a t u t goes to 1 over j omega minus a. So that means our transform is going to be equal to, we're just going to multiply it by our time shift, so we get I can make that a little prettier. Here's our time shift. And j omega, and we have, I believe it's a 3, yep, it's a minus 3. So we get plus 3. So you see that's just the time shifted version. Okay, and now we're at C, which asks us to find Fourier transform of e minus 3 t minus power 4 u t minus 2. Okay, you could use some algebra and get the Fourier transform through the properties, but one of the reasons we tabulate the Fourier transforms is for ease of use, and in this case it's not really going to be expedient to do it that way, so we're just going to use the plain old definition of the Fourier transform. Okay, so let's do it that way. So z of j omega is going to be equal to minus infinity to infinity e minus 3 t minus pi over 4. Okay, we have a unit step in our integral, so this allows us to simplify the integral greatly. For values less than 2, the unit step is 0, and any integral that has an integrand of 0 evaluates to 0. So what we're doing here, without explicitly writing it, is we're splitting up this integral into 2, and that would be from minus infinity to 2 plus another integral from 2 to infinity, in which case the integral from minus infinity to 2 is just 0, so we're omitting it. So 2 infinity e minus 3 t minus pi over 4 e minus j omega t dt. Okay, now we have to evaluate this. So using the properties of exponents, we're going to rewrite this. So we get e minus 3t e 3 pi over 4 e minus j omega t dt. You can rewrite that again. This is just a constant. Okay, so now this is an easy integral to evaluate. You should know this. Pi over 4 minus j omega plus 3 If you don't know this for some reason, what we did here was that's an antiderivative. This is an integral, so we didn't need the plus c, constant integration. Okay, so now we can just evaluate this. E 3 pi over 4. This is a negative exponent, so we're going to bring it down to the denominator and plug in infinity, in which case we get infinity now minus e 2 j omega plus 3. We kept it in the numerator this time because it doesn't evaluate to infinity. Okay, so this is 0. negatives cancel. Final answer is going to be, we're going to recombine these two here. Okay, so we get E minus 2j omega we'll keep this separate since it's the function of omega, and then we're going to combine these two. So we get E, that's 3 pi over 4 minus 6, all divided by 3 plus j omega. Okay, the reason I simplified it all the way down to this is because this is what the answer would look like if we used the properties. So while I can't say for certain you should go all the way down to here, you always want to give your answer in the simplest terms possible. So try and simplify if you can. If you're running low on time, you could probably leave it up here. As long as you know that you are going to lose points for that. But it won't be all of the points. So if you're low on time, that's a good option. Otherwise, go down all the way to here for 4 points. Okay, that was number 1.